This video is still part of the review on sequences in series, particularly on proving a certain limit of a sequence, for this case, using the definition, where the definition allows us to say that a sequence has a limit or it converges to a certain limit if for every epsilon greater than 0, there exists a natural number k. For all n greater than that k, the x sub n or the sequence satisfy the definition. The absolute value of your sequence minus your intended limit is less than epsilon. So we are going to manipulate this first before going to our proof, so that we can actually look for the appropriate expressions to be included in our proof. Let's talk about this first, this portion here. So as we substitute our sequence, you have 3n plus 1 all over 2n plus 5 minus 3 halves. Sorry, cannot see it clearly. Must be less than epsilon. So let's try to come up with an expression using without absolute value notation, and later on use that to get an expression with n on the other side. So applying here the necessary mathematical operations, you will get here 2 times 3n plus 1 minus 3 times 2n plus 5, okay, all over 2 times 2n plus 5. This must still be less than epsilon. So continuing here, again, this is not necessarily part of the proof, but this is very important for us to be guided on how will our proof will look like, or our target expression. So you will have here 6n plus 2 minus 6n minus 15 all over 2 times 2n plus 5, still less than epsilon. Let me change the color of my pen to black. Epsilon. Going further, let's leave the denominator as it is. This is 0. You will have here negative 13 all over twice 2n plus 5 is still less than epsilon. The absolute value of that is just positive 13 over 2 times 2n plus 5 less than epsilon. In short, this is one of our target expressions later, and if we could reach this is just equal to this expression, and then we have reached the definition. Hence, once we could claim this expression here, automatically that's a proof that we are doing it right, and the limit of the said sequence is what is given. Let's continue further, because we will be using n later on one side of the inequality. Hence, we can have here 13 over 2 epsilon as we multiply both sides or apply necessary factors. This is still less than 2n plus 5. So you have 13 over twice epsilon minus 5 is less than 2n. And short, finally, dividing 2 on both sides, you will get 13 over 4 epsilon minus 5 halves is less than n. We will have this as part of our expression later, again taken from that. So once we can establish this is closer now, and then definitely we will have our final part of our proof. Speaking of the proof, this is where we will start with our proof here. So proof, we will introduce an epsilon greater than 0, however small is that, it's still greater than 0, and we assume a certain k, because that's part of a definition, be equal to this expression at the bottom. Okay, this expression here, okay, this would be equal to k, 13 over 4 epsilon minus 5 halves. Okay, so let's go back here. You will have 13 over 4 epsilon minus 5 halves. Okay, now after this, let's let that be element of real numbers. But in our definition, our k should be a natural number. We cannot guarantee that k here is a natural number. Hence, we will have here, okay, n only greater than k, because there could be a value of a natural number not necessarily equal to k, but greater than k, or at least similar or almost similar to, because k is not here a natural number. This means this is equal to 13 over 4 epsilon minus 5 halves. Okay? Which implies cutting k, you will have here n is greater than 13 over 4 epsilon minus 5 halves. Okay? So, once we have this, we can now manipulate this expression. And since it is similar to what is already expressed in the denominator, we are sure to reach this part here. Okay? But of course, we are going to show that process as well. Hopefully, we could reach that. So, thus, okay? So, we'll have here n. Let's multiply both sides by 2. So, you'll have 2n is greater than, that's 13 over 2 epsilon over 5 as you multiply to both sides, which will give us then again adding both sides by 5. So you have 2n plus 5 is greater than 13 over twice epsilon. Let me change my color of my pen to black, as we have now this one here. So as we multiply both sides by a certain factor, let's say twice epsilon over 2n plus 5, to isolate epsilon on the left hand side, you have twice epsilon is greater than 13 over 2n plus 5. Okay, and then by what do you call this one, dividing both sides by 2, you have epsilon is greater than 13 over 2 times 2n plus 5. So you can see this is similar to this. We just simply exchange or change the inequality. You have 13 over twice 2n plus 5 is less than epsilon. Again, this is what it is. I told you earlier, once we reach this, ultimately we are sure that since this is just taken from this absolute value, definitely this result here is just equal to that. So we will have here hence for n greater than k, we have this expression now, this, okay, the absolute value of your sequence over, let me check, 2n plus 5, yeah, 2n plus 5 minus the limit, which is just equal to 13 over twice 2n plus 5 as indicated earlier in the process is less than epsilon. Okay, which could tell us, removing this, would tell us the final form, 3n plus 1 over 2n plus 5 minus 3 halves is just less than epsilon. And then we have reached the intended part of the definition, okay, this one here, that is equal to this. So with that, we can now claim that our limit of the sequence 3n plus 1 over 2n plus 5 as n approaches infinity converges and is equal to 3 halves. This is the end of the proof. Again, was able to establish that because we reached this one here. Ultimately, the point here is we were able to come up with the proof by coming up with these forms first. This, you consider this as part of your scratch, but this tells us the expression less than n, and more importantly less than epsilon, which is just taken from the what we need to satisfy on the definition, and with that we are guided all throughout here. Okay, thank you very much for watching.